Hi everyone, I'm Jill Riley and this is my lab 3 magnetic field of a bar magnet. So in this lab we used a bar magnet and a phone magnometer app to observe the magnetic field and distance dependence at parallel and perpendicular observation locations. This is a real-life experience, an experiment so that we can compare these measurements to an ideal distance dependence derived by the Biot-Savart law. Once we've determined the magnetic dipole from these measurements, we'll visualize the magnet's magnetic field with this magnetic dipole using GlowScript to create the model that will show this magnetic field. So to carry out this experiment, I first aligned the phones that the magnometer app read x component as 0, and did this outside to eliminate additional magnetic pull, as when I first initially was doing the experiment, the metal of my desk was creating a lot of distraction for the magnometer app. I then recorded the distances where the magnetic field matched various different values from a spreadsheet and studied the findings for accuracy in comparison to the GlowScript model. I found the following results: a distance dependence of 2.6756 and a magnitude of magnetic moment of 3.45 am squared. So some applicable physics principles used in this lab would be the Biot-Savart law, the physics principle that determines the magnetic field at different observation locations. This is shown here, and also the distance dependence relationship to the bar magnet, which is demonstrated by B bar and ln of Bx. There's also a necessary understanding of the Earth's magnetic field itself, just enough to accurately align the x component to be 0 and to understand how exactly that works. So here are my data measurements, observations, and determined dipole moment from the data. As you can see here, I recorded all of them into the system for a distance dependence of 2.6756, which was the slope of this graph. I determined the dipole moment from this experimental data at 45 degrees to be 2.83 e to the negative 5, 2.62 e to the negative 5, 2.6 e to the negative 5 for the real-life experiment. You can already tell that this is slightly off, as the z component should be equal to 0. I also found the magnitude of magnetic moment to be 3.45 am squared. So which of the statements describe what you observed? I observed that as the magnometer moves closer to the magnet, the measured x component of the magnetic field increases. You can see here my model. So we have the cyan arrows that are perpendicular to the original arrow, and the orange arrows which are parallel to the arrow. The green arrow here demonstrates the 45-degree B, and this shows my results. And though they were close, with the GlowScript B at 45 degrees being 8.34 e to the negative 6, 2.5 e to the negative 5, and 0, and a magnetic field of 8.34 e to the negative 6, 2.5 e to the negative 5, and 0, my calculated B at 45 degrees from that experiment previously was 2.83 e to the negative 5, 2.62 e to the negative 5, and 2.6 e to the negative 5. So like I said, though these are close, the z component should have been 0 in an ideal state. You can see here my GlowScript model where I identified and created arrows given this starter code, and I added in the perpendicular and parallel arrows here. So some additional questions. What if I hadn't oriented my experiment to compensate for magnetic north and had instead laid out a meter stick at some intermediate angle? The results would be off, as I would not have been able to tell which parts specifically of the magnetic field were due to the Earth versus the magnet itself, and the field would have been likely stronger. What if you were to stick two identical magnets together end to end and run the experiment again? How do you expect your measurements to differ? I believe that the magnetic field would be stronger and the distances in turn would be shorter for these measurements. Here's a copy of my GlowScript model, and I hope that you had a great time listening along and a great evening. Bye.